Hello everyone, this is Dr. Young, and in this video we're going to talk about the Hofmann elimination, how to identify when we're going to see it, and what sorts of products we get. So first of all, right, an elimination is just when you lose atoms from a molecule, right? It's not like a substitution where you switch things out, or an addition where you simply add things, right? Elimination is when you remove things. And you may remember the E2 reaction, right, from having things like, let's say we had this 2-bromobutane, and you'd add something like sodium ethoxide, maybe an ethanol. And you just at room temperatures, you're going to eliminate this and do an E2 reaction. And if you remember, there are two products you could get. I could either get the product where I form the alkene there, or where I form the alkene here. Right, remember we called these the Zaitsev versus the Hofmann product. Right, for the more stable versus least stable, right, the thermodynamic versus the kinetic product. Right, the Hofmann was that kinetic product. It's the less substituted alkene, the one that's easier, has a lower activation energy, but it doesn't give you as stable of an alkene, right? So that tends to be the smaller amount. So if you did these reactions right, you'd get like something like 75-25 for your product mixture, right? Your major product would be the Zaitsev. You'd mostly get the more substituted alkene. That's totally true. And again, if you don't remember any of this stuff at all, I would go back and review your SN1, SN2, E1, E2 stuff. Now, the Hofmann elimination is also an elimination, but it involves quaternary ammonium hydroxides. And so that's what this whole lecture is about. So if I have this analogous molecule here, only instead of a bromine as a leaving group, I have a quaternary amine. So say I have this quaternary carbon right here. And the idea is that its counter ion is going to be a hydroxide, right? So not like a bromine or chlorine, the counter ion will be a hydroxide. If you take those types of compounds and you just heat them up, you get an elimination. And it looks like just you get the same products that you would for an E2 reaction, right? Where you can get more substituted and less substituted alkene. But now, if you're pretty savvy, you may have noticed here, right, that this is called the Hofmann elimination. And we said before that we had things called the Hofmann product. It's this same guy. It's this whole idea here, where what we see happen is that if you do a Hofmann elimination, you have this quaternary ammonium on here as a leaving group instead, you tend to get much more of your Hofmann product, so 95% of that less substituted alkene than you do of the more substituted alkene. So the major products for these change, right? If you're doing a regular E2, this is your major product. The Zaitsev product is your major product. If you do a Hofmann elimination, then the Hofmann product, the less substituted product, the kinetic product, is your major product. And then just I mean, I'll draw the mechanism in a second, but the other side product for this would just be your trimethylamine and some water would be your products for these. So it's a type of elimination where you can more reliably get a bunch of that Hofmann alkene, that less substituted alkene. Normally, right, in the top example with regular old E2, we'd use a big bulky base like LDA or T-butoxide or hexamethyl disilazide or something like that. But these amines also can eliminate to give you a very large proportion of the less substituted alkene. So let's take a closer look here at what's going on. Right, like I said, the Hofmann elimination is an elimination of a quaternary ammonium hydroxide, right? So you're going to have quaternary amines and the hydroxide. You need to get that counter ion to be a hydroxide because it's going to act as the base to deprotonate, to remove the hydrogen from your substrate here. So the typical sequence that you're going to see is you're going to start with some sort of amine, like I do here, right? Here I have a secondary amine. And we need to make it a quaternary amine, right? So that's what this stuff is doing here. So I need to make it a quaternary amine by adding some sort of alkyl halide. You'll often see these methyl halides, methyl iodide, methyl bromide. Again, it's just because they react fast, and you know you're going to be able to do SN2s really, really easily. And so the purpose of that, and well, I'll draw a little mechanism here. I can show you some of this, right? So CH3, Br, right? So you do backside attack, kick those electrons onto the bromine. You get one CH3 on here, be a positive. Like we said before with that exhaustive alkylation stuff, you're going to lose a hydrogen, and then you're going to get an amine back. But then usually you have this alkylating agent, whatever you're picking here, in excess. So then you attack a second equivalent to get your quaternary amine. All right, so you've got your quaternary amine. In this case, the counter ion would be bromide, right? Because I've got Br minus from the leaving groups. Now the issue here, right, is that I need to have the hydroxide as the counter ion, not the bromine as a counter ion. So what we do here is that we then add silver oxide, silver 1 oxide. You may remember from Gen Chem that silver halides are not very soluble. They're a classic example of a precipitation reaction. And so if you do this reaction, right, you add silver halide, or silver oxide, excuse me. So Ag2O. The idea is that the silver ions attach to, in my case, the bromide ions, and they make a solid precipitate that leaves the solution. Right? They're going to precipitate out, become a solid that sits around at the bottom of your reaction flask. And then the consequence of that is you release oxides, but they are going to react with water or whatever solvent they're in, and you're going to make hydroxide. And so basically the point of this step here is that you haven't changed anything yet about the actual substrate itself, right? It's still the same organic piece. It's just now you have hydroxide as the counter ion. No more bromides anymore. They've all precipitated out with the silver that you added in that second step. And then in your last step, right, is to just heat the sucker up. So once you have the salts themselves are fairly stable at room temperatures and everything. You usually have to heat these up to 100 degrees or something like that, 150 degrees, in order to get them to actually eliminate. So you need, this last step here is a heating step. So you take the sucker, you heat it up, and that's when you do your elimination. So now you're going to treat your elimination just like you would for an E2. I am going to go figure out where my alpha and betas are. Remember that E2s were also called beta eliminations? It's the same thing here. We're going to lose a beta hydrogen. So if I look at my amine, right, where my nitrogen is, that thing's going to be the leaving group. And so one away from that amine, here I have an alpha carbon. Here I have a beta carbon. If I go to the other side, here I have an alpha carbon, and here I have a beta carbon. Right, so the alpha carbon has the good leaving group on it, right? You got a nitrogen that's positive. It probably wants to take electrons back from something. And these beta carbons, you have hydrogens on them, right? The beta carbon on the left, and I'll do this in red just to kind of, so we can keep seeing it. I have one beta hydrogen on the left, and I have two beta hydrogens on the right. So I know I can do this elimination. But keep in mind that the Hofmann is going to make the less substituted alkene. So if I go to the left-hand side of this quaternary amine, I see that I've got a methyl group on there, so I know that's going to give me at least a di-substituted alkene. However, if I go to the right-hand side, I see that I'm going to get a less substituted alkene. And I'm going to show you that with two different colors here. Let's use blue for a one-way. All right, so let's say I'm going to have the hydroxide attack this hydrogen. That means these electrons are going to drop down and kick out that way. And that would give me as an alkene here, this, right, where that was the alpha and this is the beta carbon. Now, if I had attacked the hydrogens on the right-hand side, right, one of those two, these electrons would have dropped down to give my alkene, kick out to free the amine, and that would give me that as my alkene, right? Again, where this was the alpha and this was the beta. And if you look at the two of those, whichever one is less stable, that is the Hofmann product. And so that would be the one on the right, the purple route. So I know that the purple route is the correct route because that's the less substituted alkene, that's the less stable alkene. And I'm not going to go the blue route because that's actually the more stable one, right? That would be a minor product. And so for this reaction, it looks like I would eliminate on the right-hand side. So I'd be left with my amine that looks something like this, attached to the nitrogen, two methyls, and I'd be left with this alkene right here, right? And then you'd have some water. So that would be the product of this Hofmann elimination. So the key is going to be to figure out the alpha and beta spots relative to your ammonium, and then find whichever one's going to give you the less substituted alkene, right? The less stable alkene, so you can make your Hofmann product. That's how you're going to figure out your major product. So let's look at a few examples. I'm going to go ahead and do this first one with you and then ask you to do the other three. So here's your typical sequence, right? Alkylating agent, silver oxide, heat. And so if I take a look at this, right, I'm just going to skip to what happens after step 1. Right after step 1, I should have this nitrogen here. Now going to have 3 CH3s on it. It looks like I just keep on alkylating, right? That's the whole point, is to keep on alkylating. And then after step 2, I know that there's going to be a hydroxide around. And so I just need to heat it up now to figure out what that product is going to be. And so again, I'm going to look at, well, where's the nitrogen attached? The nitrogen is attached to this carbon right here. That must be the alpha. And then it looks like I have a beta to the left, to the right-hand side, and a beta to the left-hand side. And just looking at those, right, definitely one is more substituted than the other one, right? And I want to go for the less substituted side. So if I look at this, I'm going to remove hydrogens in this case from the right-hand side. That's what my hydroxide is going to attack, right? So if I have the OH minus, it is going to attack one of these hydrogens on the right-hand side. Electron's going to drop down between the alpha beta carbons and kick out your leaving group. So when I go to draw my product over here in the box, I'm going to keep everything from the parts that were left over. Right, so now this nitrogen is attached to 2 methyls, but it's no longer charged because it got its lone pair back. And then over here on the right-hand side, it looks like I now have a double bond between what was the... Oh, wait, excuse me. See, good thing you count your carbons. I just saw a mistake. Right, I still have all of this as one carbon chain, but now the double bond's right here, and my nitrogen was freed as trimethylamine, right? Because this was the alpha and the beta carbons that I identified beforehand, right? So that's where the alkene would have formed on the less. Notice that's the less substituted alkene. If I'd gone the other way, I would have gotten a more substituted alkene. That would be a Zaitsev product, not the Hofmann product. Now, in this video, I'm not really going over why this happens. Folks are not 100% sure why you tend to get more of this less substituted alkene when you do the Hofmann elimination, but it's definitely true that you do. Probably it has to do with the fact that you have a positive leaving group, and so it makes those hydrogens more acidic, and the more acidic hydrogens on the less substituted carbon. So maybe that's why they tend to eliminate on the less substituted side, because those hydrogens are slightly more acidic when you have a really, really strong electron withdrawing group or you have a positive leaving group. That's kind of the idea, but folks are not 100% sure on the mechanism of this, so I'm not even going to really touch it. That's the most I'm going to say. For the second one, and third and fourth, why don't you pause and see if you can do this yourself? I know it seems kind of tricky at first, but if you can identify the alpha and beta hydrogens, and then you just make sure you have an alkene in between those alpha and beta carbons, you're going to be set. That's how we're going to do this. So go ahead and pause, see if you can do these last 3. So if you're coming back with me, right, this second one here is just asking for the reagents. And if I'm not wondering, well, okay, well, what kind of reagents am I going to use here? I'm going to look at the left-hand side and see, okay, well, I have an amine. And the right-hand side and see, ooh, they separated, and now I have an alkene. And another amine. And if I have an alkene and I didn't before, I know that there's some sort of elimination. Probably some sort of elimination, right? I didn't have an alkene to start with, so it's not like you did, it's not like you separated these out using ozonolysis or something like that. I had no alkene, now I do have an alkene. That's probably because you did an elimination. So I'm thinking I did some sort of elimination, and I have an amine, so it must be the Hofmann elimination, right? If you have an amine already on there and you do an elimination, chances are it's the Hofmann. So that means I just need to go ahead and be like, okay, well, on step 1, I'm going to pick a alkylating agent. I'll pick methyl iodide in this case. Step 2 is always going to be your silver 2 oxide. Step 3 is always going to be heat. And then we're set. That's what should do it. And to just kind of backtrack to make sure this makes sense for us here, if I look at this amine, right, imagine that it gained those 2 CH3s, right? Imagine it gained a CH3 here and here, right, after that step 1 and was positive. It's alpha carbon, right? Here's an alpha carbon and a beta carbon. Now I know that I definitely did not go to the right-hand side here because this beta carbon doesn't even have a beta hydrogen. So the right-hand side is out. I don't even have a beta hydrogen to eliminate. So that means it must be on the left-hand side. That beta carbon does have a beta hydrogen right here. So that's why it eliminated on that side to give us that product over there. So this all makes sense. Definitely was a Hofmann. Now, the third one is a little tricky because it involves a ring, and I know that freaks students out all of the time, but it's still the same principles, right? So if I imagine that after that first step using methyl iodide, I add one more methyl on here, now that's a positive charge. Step 2 makes it so that there's hydroxide around, right? The halogen is gone, you made silver iodide that precipitated out of the solution. And you do the same sorts of things, right? Here's an alpha spot and a beta spot. Here's an alpha spot and a beta spot. And so you ask yourself, well, of the hydrogens on the beta carbons, which one is going to give me the less substituted alkene? And so if you look at that, the less substituted alkene would definitely be on the left-hand side. It has fewer alkyl groups. So your hydroxide is going to take off that H. These electrons drop down between those alpha beta carbons. And then the nitrogen gets back its electrons from that bond right there, which is going to give me still a 1 molecule. So I'm just going to redraw this. So it's going to give me that, right? And if I had labeled, well, yeah, if you count your carbons, you'll see that that's the product that you get. I know it's a little smushed. Maybe I'll draw this out bigger right here so we can all see it together. But you should, it's not, I've said this 1,000 times, but it's never a bad idea to count your carbons. Right, so if I call these carbons, let's just call this carbon 1, 2, 3, 4, and 5. Right, notice that when I did my elimination here, I said that I was going to lose the H at this spot, right, my OH. Was going to take this hydrogen, drop down between 4 and 5, break that bond, right? That's the same thing, just a little bit bigger. And then I look over on the right-hand side, make sure I have all the right stuff. Carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, right? So there's all of my pieces. I have all the pieces. There's a methyl coming off of 1, methyl coming off of 2. Should be a new alkene between 4 and 5 because 4 and 5 were my alpha and my beta. And I drew this in a ringish sort of shape just to make sure that we saw it as being related to the starting thing. But of course, it doesn't have to exist in like a C shape. It's probably, you could have written that you have an amine, it's dimethyl, and you have 1, 2, 3, 4, 5. Right? You could have written it out like that. And again, to make sure you have the right number of carbons, 1, 2, 3, 4, 5. Right? That would have been the same thing. So you'd eliminated it, you opened up that ring. But it's the same principles, it's just a ring. So try not to freak out too much. And then this last one, we just have to backtrack to see what amine we had that we then clearly did a Hofmann elimination with, right? You see those reagents, that's a Hofmann. I think it's the only organic reagent you're going to see with a silver oxide. There may be some carbohydrate stuff, but where you're going to see some silver in it. But this is the only reaction I think so far that has any silver in it that you know of. And so we're going to definitely know that it's a Hofmann elimination. So if this was my alkene over here on the right, it must have been that was my alpha carbon and this was my beta carbon, or that this was my alpha carbon and this was my beta carbon, right? Because that's where the alkene is. That's where you had the leaving group and that's where you took off the H. So really you could draw one of two things. This nitrogen must have been attached to those spots, right, as a quaternary thing at some point in the past. And it looks like you methylated it. So these two methyl groups were not on here previously. Probably not on there previously. At least one of them wasn't. And so if I was to guess, if I was to propose something that would have led to these products, I could have done either this. I could have said, okay, if this is the red route and this was where the nitrogen was, I could have just proposed this nitrogen as the possible starting amine. Because if I'd had that, you methylate it twice, you'd get the two methyls on there. And then here's the alpha and the beta spot that would give you the less substituted alkene, the least substituted alkene. So probably that was it. Or I could have had the nitrogen here. And again, this would have been an alpha and a beta spot. That would give me the least substituted alkene possible. So either one of these two amines would have led to those two products. So here's a Hofmann elimination. You may see it, right? I'll probably ask you a question or two about it. It's classic organic chemistry. If you have any questions, please let me know, and good luck studying.